Okay, so last time we sort of changed our point of view if we move from the Lagrangian to the Hamiltonian, okay? So let me remind you the Hamiltonian H, or sometimes people, it's a function of your generalized coordinates and the generalized momenta, and then maybe time. So you see that we move from a picture in which we have the coordinates, the generalized coordinates, and then the velocities were sort of derived quantities, okay? And we live in what is called the configuration space, to a new point of view in which we really consider Qi and Pi as independent coordinates, okay? So your space is twice as big. It's called the phase space, where you have generalized coordinates and generalized momenta. And in fact, the relationship between your generalized coordinates and your momenta, remember, comes from the Hamilton equations that I write for you again. Okay, so by you have the Q I dot is equal, so I guess if I write the Hamiltonian this way, and then you have minus P di dot and in case you have an explicit time dependence, well, maybe I should stick to, you also have that. So these are called the canonical or Hamilton's canonical equation of motion. And remember that, you see, you increase the number because these are 2 times n, if n is the number of degrees of freedom. So you increase by 2, you multiply by 2 the number of equations, you have twice as many variables, Qi and Pi's, okay? These are function of t, so your trajectory is the Q of t and then the P of t, now in phase space. And you gain that instead of having second order differential equations, you have a system of first order differential equations. So it's a trade-in, as we said. I mean, it's not that you trade in some difficulties and you gain something. So you gain the fact that the differential equations are 1 order lower, but you have twice as many. So, well, it's up to. But certainly this is a powerful point of view that has been used very much, and in fact it is the starting point of most of the physics that you are going to study. For instance, in quantum mechanics, you start from the Hamiltonian, and it's the same Hamiltonian. The only difference that your Q's and your P's are operators, so are a little more complicated. They are matrices. You may wonder if you can you derive this from a variation. You remember that we derived the Lagrange equations from a variational principle. Do you remember that? That was this nice things that if you vary this quantity, right, the integral of the Lagrangian over time, the actual trajectories of motion of your systems were those for which this variation was stationary. You remember this, right? By requiring this, you rederive or you rediscover Lagrange equations. Okay, that was very beautiful, very elegant, and because it was the fact that among all the possible paths that a system can take from time t1 and t2, the actual path taken is the one that makes this integral that is called the action stationary, so an extreme, usually the minimum or the maximum. Okay, you remember that, or did you find it interesting or moderately? Okay. Well, you see, it's a completely alternative way of describing, instead of saying this point goes from here to there because f is equal to ma, you say it goes from there to there in such a way to maximize or minimize this quantity, okay? So it's, well. So how about the Hamiltonian, or better, the Hamilton's equations of motion? Can they derive from something similar? Certainly yes. After all, there is the same amount of information you have here is the same that you had in the case of the Lagrangian. And in fact, if I replace the Lagrangian by, you remember this Legendre transformation, I can rewrite this variational principle from these two times, so T1 and T2. So L, you remember, is just P Q dot I sum, Einstein sum, minus the Hamiltonian, that itself is a function of this. So if I rewrite this, I just rewrite the Lagrangian is identical. This is the Lagrangian. So I just replace the Lagrangian with the Legendre transformation that usually we wrote as H equal this minus the Lagrangian, but I certainly can move my terms from one side to the other. And I do my variation, right? That is the variation of along all possible paths with the constraint that I keep the two end points, T1 and T2, fixed. Okay, if I do that, you understand that you get the same. So, I mean, this is the Lagrangian. So, let me call it F, this quantity, now. And you see, the only difference here is that I'm doing my variation not only under the generalized coordinates, but also the generalized momenta, right? So I have two sets of Lagrange equation. One for this, right? And the other when here I have the p's. So I'm just redoing what we did several weeks ago. I know that the condition for this variation to vanish, meaning that this is a stationary point, is exactly the Lagrange equations. And the only thing I have to remember here is that now I'm doing the variation not in the configuration space, but in the phase space, because I have Q's and P's as independent variables. Therefore, I have twice as many Lagrange equations. I have the one with respect to the Q dots and the Q's, and the P dot and the P's. Okay, but you see that if you look at this, so F is this quantity. You see what is this dF dQ dot, right? The Q dot. You see that is just the pi, right? So this term, this term here is just the pi. So if I take the, well, it's just the I guess pj, but pj. And what is this? You see that the only dependence on the QI's is in the Hamiltonian. So this is just the dH dQj. How about this term? There is no dependence on the P dots, right? Because there will be the acceleration. In general, you don't have a dependent. So this is just not there. And this one has two terms, right? This one, it has this term and this term. So this one, this equation here, leads directly to the first of these, because you see this is Q dot from here, Q dot J now, right? Q dot J minus dH dPj must vanish. You see this is exactly this. And this one here, so this, you see this is Pj, so you have P dot J minus dH. Actually, there is a minus here, right? So it becomes a plus. dqj equal to 0. That, I guess, is this one here. So indeed, from the same variational principle, and therefore from the same point of view, I can derive now the same way I derived the Lagrange equations, and actually I'm just using the previous results. I do regain my Hamilton's set of equations. So the canonical equations can be derived from a variational principle as well as the other. In fact, here there are many variations that you can apply to this or other quantities, and okay, we don't have time to discuss that. But if you go to your textbook, the Goldsteins, you will see that there is also a thing that is called the principle of least action. That is the traditional way of discussing these variational problems leading to dynamical equations. So if you like the subject, you can go and read about it. It's just a more general variation of the action, and you derive something similar. So okay, well, it would be nice to discuss. But so beside that, what I want to now do is I want to solve these equations, okay? And so on Friday we have problem solved, right? So how was the test? It was interesting. You have already enough problems, right? Or you want more for Friday? Okay, but so then on Friday, maybe I'll give you some extra problems that we won't solve together, because otherwise you haven't solved any problems on the Hamiltonians. But certainly, usually the final test is like 3 problems or 4, and one of them is on the Hamiltonian. I mean, okay, I forgot if 4, 3. We'll see. Did you decide when to have this? You haven't decided yet. Did you or did you not? Okay, but try to converge on some date. Okay, so let's. So we have our canonical equations, and so I don't want to. I'll give you some problems that you can try and solve, some specific problems. But here I don't want to discuss some particular problem that we can solve. I mean, all problems that you have solved using the Lagrangian, clearly you can solve them. I show you like the pendulum and some other stuff. But by looking at these equations, you can see that there is a systematic way to try and solve these equations. And the way it was already hinted by what I said last time, right? Because remember that if you have a cyclic variables, right, like you had in the Lagrangian, meaning that the variable does not appear. So you take one of the q's here, and your Hamiltonian does not depend on these variables, right? That's the definition of a cyclic. Okay, that was nice, and it was useful within the Lagrangian approach, but here, I said, is even more powerful, because if you have this property, immediately the corresponding momentum, because by assumption this goes to 0, it vanishes. So from this equation, I obtained the fact that the corresponding conjugate momentum of these 2 canonical variables is conserved, right? And this was true, obviously, also in the Lagrangian context through the Noether's theorem. But here, it's, in a way, it's even more powerful because now the momenta are themselves variables. So that means if you have a cyclic variables, it's like a double, you pay 1, you get 2, because not only it does not depend on the QI, but the corresponding momenta is also a constant. So what would be the ideal situation? Well, the ideal situation is that if you have all cyclic variables, because you understand that then the Hamiltonian is just a constant, because it's a function of constant, and a function of constant is a constant, right? So how nice would that be, right? If for each problem you were able to change your variables in such a way that they were all cyclic and all the momenta constants. Because that means what? Let me call, so if a variable Qi is cyclic, the Pi is constant, and I call it alpha I. Usually alpha is a constant, but not always, but in this context. So if is this the situation, so I say the ideal situation, right, would be all Q sub i's are cyclic, cyclical variables, meaning that they are not there, okay? Then I said the Hamiltonian is just a constant, right, because you have all the Pi's are just alpha I, and then the Hamiltonian is so it's not a function of the Qi's, because by assumption I'm assuming that it's not, because otherwise they would not be cyclic. And therefore this is alpha 1, alpha 2, alpha n, right? These are all constants. This is a constant. What happened to the Hamilton equations of motion? Well, they become very simple, right? Because one is the things that this is a constant. And the other one, you see, this is a constant, so it's just a derivative of this constant. So it's just the Qi is just dh d alpha I. That can only be a constant that I call omega I. So it's a constant in time. This is really the best of all possible worlds, because this is a trivial equation, and this is too is as trivial as that, because this is not, you can integrate immediately. Qi as a function of t is just omega I t plus maybe some integration constant that is another constant that I call beta. So you have solved the problem. If this is the situation, I call it ideal, because immediately you can integrate the p is p, so pi of t is a constant. So those are your trajectory in phase space. The p stays whatever is the initial value, alpha, and the Qi's are just a linear function of time with these two constants. So what I'm saying is that if this is the case, then you don't need elliptic integrals. You don't need any. You don't have to read that book that I'm pushing every day, trying to sell it. You don't have to need Mathematica. You can, any 4 years old can solve. Well, maybe not a 4 years old, but any teenagers can solve that set of equations. Okay, so that would be great. We have a question. Okay, yeah, I'm assuming also that energy is conserved. So I'm assuming that also T, you see, I'm saying all cyclic variables, so I'm assuming that also T is cyclic, so that, yeah, otherwise you have a time dependence there. But, okay, so this is nice, it's really exciting in a way, but so practically what can I do? Well, clearly, very few systems can, for very few systems you can do that, but for any system, you can try to do a change of variables, because you understand that the number of cyclic variables depend on the choice of coordinates, right? Remember that the trivial example is a spherical symmetrical system that you describe using Cartesian coordinates. You don't have any cyclic variables, right? Because, however, if you go to spherical coordinates, immediately you find a lot of cyclic variables, right? You see, so your choice of, this was where we started from. Both the Lagrangian and the Hamiltonians are very powerful tools, but so that once you write them down, then you have a protocol that you follow, and you end up with your solution. But the catch is, or if you want, the complication is conserved after all, because you must be clever in choosing your generalized coordinates. And here is even more true. Here you have to be clever, because the more clever you are, the more cyclic variables you have. And ideally, if you are so smart to make all your variables cyclic, then you are done. Like, 5 minutes after I give you the problems, you walk out. Right, ideally. So so the question, you see, instead of solving differential equations, now you have to try to find these coordinates, and you have to relay on the, so what kind of change of variables are you allowed? This is the question. Okay, actually, it's a very large set of transformation, and so I want now to talk about what kind of change of variables you can perform and which one you can. And so I want to change from an original set of variables that I call little q's and little p's to a new set that I call big Q. So these are transformations. So let's assume that big Q's is a function of your original set of variables, maybe even time. So here I should put some index, but and new big Pi is a function of your original Q's, P, and T. Okay, so this is just the definition of a transformation. So just a change of variable. For instance, I decide that all my coordinates become momenta, and all my momenta become coordinates. That's perfectly allowed. I switch them over. Or the Q's become a sign of P, and very general. They are very general transformations, and these transformations are called canonical. Everything here is called canonical, and so those are the canonical equations, and these are the canonical transformations. And the only condition that you have for a transformation of coordinates to be canonical is that at the end of the transformation, it exists a function that you call k, such as you can write your equations as Hamilton equations, right? In the new variables, obviously. So this, I guess, is a capital K. I don't know how to. Everything is capital in the new. So this is the definition of a canonical transformation. So it's a very large set of transformations, but it's not all possible transformations. There are transformations that are canonical and others that are not. And you are allowed to use only canonical transformations in order to hunt for cyclic variables. And you understand that this condition is that the one that guarantees you that in the new variables still the Hamilton's equations hold, right? You don't want to do a transformation that ends up with not having the same dynamical equations, okay? So that's the condition is exactly that. But this is a very large, as you will see, we will discuss some possible transformations. So actually, how do I go about, so this you understand. So let's start again from the left side. So if you, so you will see, I mean, there is a standard way to characterize these canonical transformations, and it comes from the fact that, you see, if you look at this definition of big K and big H that I remove, you remember they came from this variational principle, right, that I rewrite here. If you had your original Pi Q dot I minus the Hamiltonian, right? And if this is true, then now you have the same for the big guys. So big capital P, uppercase P, uppercase Q's minus this K that is the new Hamiltonian in the new capital uppercase canonical coordinates. But you see, if these two must hold at the same time, that means that these two integrands can, I mean, these two, they can only differ at most for a total derivative with respect to time, meaning that this is equal to this, except for a total derivative of a function that I don't know, an arbitrary function. I mean, the total derivative of an arbitrary function. This may be obvious or not. It's an exercise in your textbook to prove that this is true. So probably I didn't assign it because we didn't have time. But just take it for either you convince yourself doing the exercise, or just take my word for that. So what I'm saying that this is equal to this function here is equal to this function, except for a total derivative of a function. Okay, this comes from the. You can convince yourself by going through this. Actually, this is the same reason why two Lagrangians differing only for a total derivative of a function, they lead to the same equations of motion. Okay, I think this was the exercise that I should have asked you to solve, but okay. And actually, this is quite useful in certain situations if you go back now to the Lagrangian approach, because you understand that may help in shifting the value of the Lagrangian, and or maybe if you write a Lagrangian and you identify a sub-piece of that Lagrangian to be a total derivative of a function, then you can drop that part and you will have the same equations of motion. So that may be useful. Okay, but then you understand that if you know this function here, you know the transformation, because these two differ only because of this function. So this change of variables is characterized exactly by this function that is the difference between these two sets. So in other words, if I know f, okay, I know the transformation. The transformation meaning this, the canonical transformation, okay? And what is the f? F must be a function of the old and the new variables, okay, because it's linking these two and it's completely characterizing the transformation. So it must be a mixture of what? Can be either a little q and a big Q, sorry, and of course t, or can be so you have four possibilities, right? Can be little q and big Q, or little q and big P, or a little p and big Q, or little p and big P. So you have 4 possibilities, and usually in the literature they are called F1, F2, F3, and 4. And you see that so you have these 4 possibilities. Then, as I said, by definition, you have the pi qi dot minus h is equal to big pi, big qi dot minus k plus this total derivative of f of t. So what I'm saying is now, by this requirement that is built in this definition, if I specify which f I have there, I can force this to be true and find differential equations through which I can find my f. And if I have f, I generate the canonical transformation. So this is the set of equations that you are supposed to study, not to find the equations of motion of your system, but to find the canonical transformation. So that's useful because we are looking for canonical transformations that bring my system into that nice form in which most of the coordinates are cyclic. So for instance, let's look at the case in which I have the f1 function. You see that this is the total derivative with respect to f, and f1 is a function of little q, big Q, and t, right? So what is this total derivative? Well, it's the usual story. I can always write the total derivative of a function as the sum of the partial derivatives, right? So it depends on q. So this is a 1, this is a I know. Q dot I plus df1 d big qi dot plus maybe df1 dt, right? This is always true. I assume this from day one, so don't tell me please now that is last day minus 3 that you don't understand that, because otherwise I leave. So this is always true. So now I can look and try to see what equations this f1 must satisfy in order for this to be true, right? And you see immediately, you see this is h, this is k. Here you have q dot, big Q, and here you have little q dot, okay? So you see these coefficients must match. So that means that this pi must be equal to what? P, right? And this big pi must be equal to the other guy. Actually with the minus sign, right? Because it's on the other side. And then whatever is left must be equal to this. So if I do that, you see I get 3 equations. I get that pi must be df1 dqi, then the big pi, capital, uppercase, whatever, minus df1 dqi, and finally whatever is left, that is h, k, and the derivative, the partial derivative with respect to the time of the function f1. So that means the k is equal to h plus df1 dt. So you see I have n equations that if I solve them, I get the big qi's as a function of little qi's and little pi's. Okay? And the same for the big. So by solving these equations, I get exactly my canonical transformation. Okay, so this is the trade-in. Instead of looking for the equation of motion, now I look for these new equations. I solve them by finding this function f. By the way, these are called generating functions. for obvious reasons, right? Generating functions because they generate the canonical transformation. And of course, the specific forms of these equations depend, you see, it depends on which function you have. So this set is okay for the generative function that I call f1. How about f2? Well, you just go through the same steps, but now with f2. Remember, f2 is a function of little q and big P. So instead of having this, here you have big P, right? And then you have to compare. And you find the new equations. Or, what is another possibility? The Legendre transformation. You see, you go from f1 to f2 by exchanging these two variables. So if you remember your Legendre transformation, f2 must be what? So, well, actually, well, it depends on the sign. f1 is equal to f, so f2 is f1 plus the variables that you are switching. So f1 is f2 minus the variables that you are switching. And then you plug in there this, and you get the new equations. Okay? And the new equations, let me write them for you, is pi is equal to f2 qi, and now you don't have the big pi, you have the big qi that is equal to plus f2 little pi. No, big pi. There are, and this is still true. Okay? So if you go to your textbook again, you find the same for F3 and F4, and you get all four sets. So you should bear in mind those different equations. Let's just study some simple examples of this canonical transformation so that you get some feelings for how they work. Let's take the simplest example, for instance. Well, I should have kept these equations, but okay. Take a generating function that, of the kind f2. That is the simplest, just the product and the sum of qi big pi. Now remember the f2, I said that pi is equal for f2 df2 dq1 big qi is dpi, and the Hamiltonian is just, right? So usually here students ask, well, should I memorize all these equations, right? That's a reasonable question. Okay, the answer is no, because if I ask you that, I'll give you the equations in the problem, okay? But of course, you are welcome to memorize these four sets. You need to memorize 4 sets of equations. This anyway is for F2. Now, so if F2 is equal to that, what is Pi?
Big Pi.
Is what is big Qi? No, no. And what is K? H. So this is, what transformation is this? Well, it's canonical, okay, very good. But, I mean, little p goes in big P. It's an identity, right? So it's the simplest transformation. I just changed the name from lowercase to uppercase. So this is the, well, okay, no big deal. But what about if I take for F2 this one? Here I take a generic function of the Qi, okay, and I multiply by big Pi. So the identity is gone. Right? So I take F2 to be just any function of the little q's, okay, a different one for, and then I multiply by big P. So what is Pi? Pi is, no, it's not 0.
No, df by dq times big.
Yeah. So the most interesting is this one, right? Because you see Qi, this is this arbitrary, no, it's not 0. Is this arbitrary transformation. So this is an arbitrary transformation, so it's just a point transformation. So, okay, any point transformation of your coordinates is a canonical transformation. That means no matter what kind of transformation you do, you take a, well, it's up to you. Any transformation, any point transformation of your coordinates, you know, to transform to the new ones is a canonical, so that's very good. You can really, well, you can really transform. And how about last example, last trivial example at least. I take of the kind F1. So this is Q. So I take Q, K, big Q, so the product of the well, this you already know in a way because you see it's like a Legendre transformation, but let's do it. So you see now I have the wrong equations, right? Because I want the one for the F1, so that's why. So it was little. This was the same, right? Because and this one is the one that is big Pi. And here you have big Q. And this is this. So what is this transformation? Well, this goes into big Qi, right? And this goes actually there is a minus here if I remember correctly. So here you get minus Qi. And here is just the Hamiltonian. So the Hamiltonians remains the same. The Hamiltonian always remain the same unless you put an explicit time dependent here. And what the transformation is this? It's just, as I said before, you can always trade in. You can always trade in your coordinates for the momenta and vice versa. So if one morning you decide that instead of using your coordinates, you want to use the momenta and vice versa, that's okay. It's a canonical transformation. You are guaranteed by this construction that this is going to be canonical. Yes?
The other one.
Which one? The one, the point function, yeah. So this was of the type F2, and I took any point transformation, right? So, but only of the coordinates. Actually, I took even time dependent, so you are going to have a shift in Hamiltonian. But okay, let's forget about this. And I multiply this by the big Pi. Then here you have 2. Here this is switched to the Qi, I guess, big Pi. Okay, so here you are going to have some complicated function that is the derivative of this, right? So, okay, it's whatever it is. But I'm interested in what happened to the big Q, the new coordinates. You see, they are simply whatever point transformation you had here, because you take the derivative with respect to the big P, and you are left with this. So this is a transformation of your coordinates that is arbitrary in a sense. It's a point transformation. So any transformation you can think of, almost. You know about point transformation. So the point, you just have x, then you take any function of this x. This is a point transformation. You take any function. It should be a reasonably well-behaved function, but in the real world, all functions are reasonably well-behaved. I mean, you know, those pathological cases of functions you find only in the mathematical textbooks. They don't live outside. They are useful to test theorem, but then yeah, okay. And of course, you have to compensate somehow for this to be a canonical. So here you get actually something that is complicated because it's the derivative here of this function with respect to this times the dpi. So this may be complicated. But the point here is that it allows you to think, at least in principle, that any point transformation of your original coordinates is an allowed canonical transformation. So it's a very powerful tool. And should we look at some real-life example? Yes, of course. So for instance, how about the harmonical oscillators? Okay, I know that we already solved that. So by now you have solved that problem using f equal to ma, I hope, not here but somewhere else. We have solved it using the Lagrangian. We want to solve it using the Hamiltonian, right? But not by brute force, but by finding some interesting canonical transformation that makes this problem into a very simple one, okay? So let's do that. So first we have to write the Hamiltonian. What is the Hamiltonian for an harmonical oscillator? So how do I write an Hamiltonian? Right, for instance. Therefore, what is the kinetic energy then? But I have to write, yeah? Right. Are you all on the same page, or is that obvious? Okay, very good. Okay, how about the other term?
And some frequency q square.
Okay. Or, let's do it like this, for instance, first. If I have a spring with the spring constant k, okay, should I say more? No. Then let's write it in a nice way. I guess the quantum mechanical way is to introduce this omega, right? Omega square is equal to k over m. So I pull out the mass, and here I get this famous factor m square, omega square, q square. Very good. This is the Hamiltonian for the harmonic. In a way, this is the most famous and most important Hamiltonian that you will ever see. Because we already discussed, because of the small oscillations, you see everything comes together. This is very important because any system in any potential, when you do a perturbation about a stable position, it will behave as an harmonical oscillator, right? So many, many systems you can discuss. And in fact, most of, say, 70% of physics is about the harmonical oscillator in various different situations. Okay, so you can perfectly fine, in fact, I encourage you to do it, just write the Hamilton's canonical equations for this system and, you know, plug in, solve them, and you get your usual solution in terms of trigonometric functions. But since we just learned that if, you see here, is there any canonical variable, cyclic variables? Well, this is a one-dimensional system, and unfortunately, Q is there, so Q is not, okay, so, but, question, can I find a new set of variables, big Q, big P, such that this guy has no dependence on big Q? If I do that, I'm very happy, right, because the Hamiltonian becomes a constant, and I know how to solve a problem. You know, it's trivial. We just discussed it in that case. So how about this transformation? Well, I have to find a generating function, right, to be sure that this is a canonical transformation, that makes generate the canonical transformations such that this system becomes a constant, in other words. Okay. Actually, you see that there is a sort, when you write it in this form, so, okay, now the question is, how do I find this function? That, of course, is a difficult question. There is no easy way. You have to guess this function. So here is where, But, you see, here you have a sort of a hint. Because, you see, this is p squared plus something plus q squared. And by now, you should remember that if you have square plus square, if that something is a sine and the other something is a cosine, if you get sine square plus cosine square, that's very good because that's 1. It's a constant. So in a way, if you find a transformation such that p, little p, goes into some function of big P and big Q's, such that is, well, let's say, a sine of big Q, and this is the cosine of big Q, and somehow you get rid of that constant, then you get 1, maybe with some, and then you are done, right? Okay, so here I come in, and I tell you that to take f1, so if generating function of the type f1, so it depends on little q and big Q, and, okay, it's a weird object, is this. But, okay, why? Well, we are going to see why. What are the equations that, so I only have 1 degree of freedom, so I only have 1 q and 1 p. And remember that little p is the partial derivative of this generative function. So this is the generative function with respect to little q, right? So, okay, I give you the f1, so we do together the partial derivative. So what is the partial derivative with respect to little q of this? Well, this is trivial, right? Is m omega q, and this is whatever it is, because I'm not. And what is big P? Uppercase P is minus, remember, or if you don't remember, I tell you. It's right, so you have to take the derivative of the cotangent. So it's m omega q squared divided by 2, and I tell you that the derivative of the cotangent is 1 over the sine square, right? Minus, you're right. So that takes care of that minus there. And there is no time dependence, so I don't have to worry. The Hamiltonian is going to be just the Hamiltonian. So what I want is, you see, now I'm looking to k. So k is just h. There is no partial derivative because there is not explicit time dependence here. So all I have to do is to write h in terms of these big q's and big p, and then I'm done. So let's try this. To do that, so p, little p, I already have it in this form. So I need little p and little q in terms of big P and big Q. Okay, so you have to solve this, and if you do that, you find that little q is the square root of 2 big P m omega sine of big Q, and little p is 2 big P m omega cosine of big Q, as advertised. Because if I now take this and I plug it in here, you see that you get exactly omega big P. So you see now the Hamiltonian is what? The Hamiltonian is, there is no dependence on big Q. So Q is a cyclic variable. Big Q is a cyclic variable. Therefore, big P is just a constant. The Hamiltonian is just a constant. And now to write and integrate the Hamilton equations is exactly something that you can do in one line. Because what is the, so this is actually, to be careful with the notation, this is your new Hamiltonian that we agree to call big K. So what are the, so big Q dot is equal to the partial, these are the canonical equation of the partial derivative of K with respect to P, right? And big P is just minus the derivative of K with respect to big Q, but by construction this is 0 and P is a constant. So I only have to integrate this, but this is really simple because it's just the derivative of this is a constant, so this is just omega. And therefore, Q as a function of time is just omega times t plus whatever Q naught, or let's call it alpha, that is the initial at time equal to 0, what is the value of Q, right? The initial coordinate. This is the solution. You see, you have, and if you plug in back in here, what happened? P is a constant. What is this constant, P? It's just the energy, right? Except for this omega. Because the Hamiltonian is the energy, right? So this is the energy. So P is the energy divided by omega. So I can rewrite this as the square root of twice P, we said, is the energy divided by omega. So it's this. Sine, what is big Q, is this. Omega t plus the initial value. And this, you see, is the nice old friend, the sign that is the solution of this problem. You see, I found the solution with no fancy integration, no integrals. This is all trivial. This is the derivative is a constant, so just I have to take the integral of this, but this anybody can do, and I have my solution. So everything is nice. Everything looks very simple. But remember that I gave you the F1. If I didn't write that down, probably the amount of work is conserved, right? Is related to some cyclic variables. The amount of work to solve a problem is somehow conserved through all procedures. But of course, as you go on, you understand more about what is behind these systems because you understand more mathematics, the way they behave. You see, this is a nice way to solve the harmonical oscillator. And it tells us something interesting.
So, what are the most common techniques to extract the generating function?
Well, actually, there is no systematic, that's unfortunately is the problem. There is no systematic way. You have to guess. But, okay, but yeah, I think at least I don't know of it. But there are some, how to say, some aids, right, to do that, and we will talk of some of them in a second. I just wanted to decide what to leave as an exercise and what to. Well, let me introduce some more tools, and then we come back to this kind of problems. I mean, the short answer to that is the following. No, the way I'm not answering right away is because I'm not sure I want to enter this, because the answer to your questions is the third way to solve problems in classical mechanics. I know, I mean, it never ends. Because there is a technique or a set of equations that are called Hamilton-Jacobi equations. Maybe you heard about those. I mean, you did, okay. Where? In what? On TV? No. In your class, of course. That exactly this. I mean, it's a set of differential equations that if you solve them, you find the generating function for the canonical transformation that brings the system in this very simple way. So that's the answer. That's the short answer. So usually I do that, but I'm not sure we will have time. So, okay, let's see. Maybe Wednesday is the last lecture. Maybe you have the choice either. So usually I either solve a simple problem using all possible techniques. So that's usually nice. It's a big hit. Or we discuss this Hamilton-Jacobi business. Of course, if I do the Hamilton-Jacobi, then I can solve the problem also using the Hamilton-Jacobi. So, well, let's see. Let's see how much we can do today. But, okay, that's the question. Of course, people ask themselves, okay, now I have this nice technique. How can I find this generating function? So there is no general way. The only general way is to solve these differential equations. Unfortunately, these differential equations are very complicated because they are differential equations with partial derivatives, okay? And those, they don't have general solutions. So for each case, probably you know, there are classes, okay, that if we do it, we discuss that. Of course, it boils down to the following. So this is the takeaway message. Those problems that admit an exact solutions, they have an exact solution of the Hamilton-Jacobi, obviously, because then you will, it's like this one. This clearly, I mean, you didn't need all this stuff because you knew that, you knew the solutions. But this way you learn something more, and this is the case. So if you do the Hamilton-Jacobi equation for the harmonic oscillator, the solution is this F1. So, I mean, it's not that I wake up one morning and I wrote that F1. You solve the Hamilton-Jacobi and you find that F1. Or you look it up in a book or on the internet or whatever. So let's see how much we can... I mean, Hamilton-Jacobi, I mean, usually students hate it. So for a few years I was doing that. And then I stopped because they thought, well, I mean, it comes at the end, you know, everybody's tired. Why should we learn all this stuff? But the point is that actually that would be the best way to introduce quantum mechanics, because probably you've done that too, maybe. Because the Hamilton-Jacobi really, it's a smooth way to Schrödinger equation. And that's the way Schrödinger, I mean, how Schrödinger came up with the Schrödinger equation, through Hamilton-Jacobi, essentially. Can we do it now? No, I mean, no, that I never do because that's really quantum mechanics. But if you know the Hamilton-Jacobi, you understand how to get the Schrödinger equation. Because usually Schrödinger equation, they write Schrödinger equation, they say, you know, this is the equation. Okay, but why? How did Schrödinger came up with that? Schrödinger knew classical mechanics and he knew Hamilton-Jacobi, and it's a nice path to do that. Okay. He was he was a conservative guy. I mean, Heisenberg was really a revolutionary because he introduced this matrix stuff that really was never seen before. You know, he really had the idea that you have jumps, so you have numbers. So you should write somehow the Fourier transform with matrices. So that was the Heisenberg approach. Schrödinger was more, he liked classical mechanics, so he worked with this concept. And then they showed that, you know, these two approaches, right? Either you solve the Heisenberg matrices, you diagonalize matrices, you find eigenvalues, or you study the differential equations that is Schrödinger, you find the eigenvalues. So they are equivalent, but conceptually they're very different, right? But people like very much Schrödinger equation because they knew about this stuff. So, you know, when you know something, you want to use what you know. You don't want to learn something new, like yourself. So people didn't want to know, you know, now I have to study the matrices. So they say, no, I study the differential equations I know already. So that's only human. But this we cut. Non lo mettiamo nel filmato questo. Okay, so what else do you need to study canonical transformation? So let me introduce another thing that, by the way, is related to quantum mechanics as well. These are called Poisson brackets. So I introduced those things because if you go and study more, you need to know what they are in order to. So this is just a handy way to see. Very often in this business, if you have two functions of your canonical variables, very often you end up taking this kind of derivatives. So this particular combination of derivatives. So Q, P, P, Q. Okay, so U and V are functions of your canonical variables, Q, P, as many as the degrees of freedom. And very often you will see you end up having to compute this combination. First you take the partial derivative with respect to Q of the first function, then the second function, and then the opposite. So this combination, Poisson decided, since he had to write this several times every day, he decided to call the shorthand. So this is called the Poisson bracket. So if you see this symbol, it means this. So I guess I should write that. Okay, so why bother? It is possible, but we are not going to prove that. It's possible to prove that they are invariant under canonical transformation. So it's a quantity that is invariant in form under canonical transformation. So it's interesting because if you compute this quantity, then it remains the same under canonical transformation. So it may be useful. It may be not. Maybe we will see. Okay? And just by the definition, you see that the Poisson brackets, they satisfy some I mean, it's easy to prove, right, but just by inspection, that if you take the Poisson bracket of the same function, that vanishes, obvious. If U is equal to V, you have just written. And then they are, and then they are anti-symmetric, you understand. If you take U Poisson bracket of V, this, you see, if you switch V with U, you get the minus sign, right? So it's anti-symmetric. And also, you have a linearity transformation. That is, if you take A, U plus B, V of another function W of your canonical transformation, then this thing is A, U, W plus B, V, W. So it's a sort of linear property. So they behave linearly under a linear transformation. Okay, that's maybe a little formal, but it may come useful. Now, why Poisson was getting these terms all the time? Well, it's easy to understand. Take a function, any function, of your canonical variables, so let's call it U, and take a total derivative. The same that we did half an hour ago. We took F1, for instance, and I computed the total derivative. That we know how to do, the U, the Qi, Q dot I, right? U is a function of Qi and Pi, right? Of your canonical transformation, and maybe also T, why not? Plus the U, dPi, P dot I, of course also du, dt. So I wrote the total derivative of a function of Q, P, and T in terms of the partial derivatives, right? But now these are canonical variables, so this Q dot is equal to what? Q dot, if you recall Hamilton equations, is the partial derivative of dH, right, with respect to Pi. And P dot is minus the partial derivative of dH with respect to Qi. So you see that the total derivative of this function can be rewritten as du, dQi, dH, dPi, minus du, dPi, dH, dQi, that by definition and now you understand why Poisson was getting all these Poisson brackets, is the Poisson bracket of your function and the Hamiltonian. Yeah, because you also have this, so plus du dt. You are right. So the total derivative of a function of your canonical variable can be written as the Poisson bracket with the Hamiltonian plus, as he pointed out, in case it depends explicitly on the Hamiltonian, that. And also, you see what happens if this quantity happens to be a constant of motion that is conserved. Then, by definition, this vanishes, and therefore, a quantity that is a constant of motion, you have that this vanishes. Therefore, you have that for a constant of motion, the Poisson bracket is just equal to du dt. What happened to the minus sign? Very good. What happened to a constant of motion that does not depend explicitly on time? Then this is gone. Therefore, a constant of motion that does not depend explicitly on time has Poisson bracket with the Hamiltonian vanishing. It commutes with the Hamiltonian, if this sounds more agreeable. So in a way, this is another way you can discover constants of motions, right? You check. It has vanishing Poisson brackets. It does not depend explicitly on time. That quantity is going to be a constant of motion. You studied the Dirac brackets in quantum mechanics, did you or did you not? The Dirac brackets, yes, no? Here, in George's class, yes? Yes or no? Do you all take the same class? What? Second term, okay. So you will need this because Dirac's bracket, Dirac was another guy who loved this stuff. So the Dirac bracket is directly related to the Poisson bracket. So that's another reason why you need those. How about now, okay, here. Now that I know about, so let me drop this QP here. I mean, it's implicit that we are studying functions that are with respect to canonical variables. You see immediately from the definition that if I take the Poisson bracket of the canonical variables themselves, so Q's and P's, what happens? If I take a Poisson bracket of two Pi, Pj canonical momenta, you see from here, right, what happens? They vanish. In fact, they are equal. Right? Because now U and V take P, P. So each time you have a missing, so it vanishes. Same if you take Q, Q. The only case in which they do not vanish is if you take first a Q and then a P, like this, Pi, Pj. And in fact, the only case in which you don't have a vanishes quantity if these two indices happen to be the same. And so back to the Kronecker index tensor. So these are called Poisson fundamental brackets, I guess.
Sir,
Yeah.
what if u depend on t, but the total derivative of u with respect to t is equal to the partial derivative of u with respect to t?
So wait a second. You want u to depend on t explicitly.
Yeah, u depend on t,
Yes.
and du by dt is equal to the partial derivative of u with respect to t.
Well, then it means that it's a conserved quantity, right?
Yeah, but u depend on t.
No, but that's always true. U depend explicitly on t.
Yeah, but the
That
bracket can be zero.
No, I mean, if u depends explicitly on t, this is true, right? And this is true.
Yeah.
So that's all.
Okay.
What is the additional information you want to put in?
Yeah, if u is does not, if u depend explicitly on time t,
Then you have that partial derivative that is not zero.
yes, and if the partial derivative is equal to the total derivative, then the Poisson bracket
Vanishes.
And so we have two situations where u is a constant of the motion.
No, it's a constant, so you want. Wait a second.
The only option,
So you want this to be exactly equal to this, with the minus sign in such a way that that goes to zero? No, I'm not sure I understood.
okay, let's say if
So you want this equal to zero and this equal to zero.
no,
So then is this?
no,
No?
yeah.
W-
Both are different from zero.
Wait.
They are equal.
So du dt equals,
The partial of u. Yes.
that's all you want.
Yes.
Well, then that implies that this is equal to that.
Yeah. So
If this is true, that means it only can be true if this is zero, right?
zero.
Yes, because look. I mean, this is only true if u depends only on t, right?
Yeah. Yes. And then so we have two options for.
So 0, 0, that means that this is 0 too.
Yeah. So we have two options, not only just one.
So then
Say
u,
the constant of the motion.
I know, because, so you say, but this is equal to this, but not equal to 0, right?
Yes. Yes.
So that means that here you have that, well, clearly, then h u is equal,
Zero.
no, is equal to this.
No, we say du by dt is.
But so then you say this,
Ah. Okay.
and then, no, if this is true, but not equal to 0, then this is equal du dt. It's just this case here. If this is equal to 0, then that's equal to 0. No?
Yeah. Yeah.
You think there is a third?
If we say du by dt is the Poisson bracket plus the partial of u.
No, but the total derivative, equal partial derivative, is equal to 0 or not?
Not zero.
Not 0.
And
Okay, then this is true. And is also equal to the total derivative. So you're back here. Then it means that I see. You say then it means that okay. Yeah, but this is okay, is what I said here. Right? Because this means that the Poisson bracket of h, no, is equal to 0. So that it means that you cannot have this. So that's So these are the fundamental Poisson fundamental brackets. And now you understand you can also write Hamilton's equations using the Poisson bracket, right? Because you have, yes. Other questions, or it's just, it's about this or something different? And then you can tell. If it's different, it's your own business. But otherwise, we can hear about it. No, okay. You see that now I can write, yeah, let me finish because otherwise I can write, you see, use this, you see this is dH, dPi, right, is equal to Q dot I. So you see this is I'm writing the Hamilton equations, and I can write also the other one, PIH minus dH dQi equal P dot I. So for the canonical ensemble, you have a very first of all, canonical variables satisfy this, they commute or whatever, they have Poisson brackets vanishing if you among themselves, and then you have this nice relation that only the conjugate momentum has a non-vanishing Poisson bracket with the corresponding coordinates. Moreover, you can easily, just plug in Q and H here, and you get the Hamilton equations for the case. So the Hamilton equations can be written as the partial derivative of H with respect to Pi equal to the Poisson bracket of the canonical coordinate with respect to H. And vice versa, and the same for the other canonical variables.
Sir?
Yes.
If the converse always true, I mean, if the Poisson bracket is invariant under a given transformation, then can we say the transformation is canonical?
That preserves the Poisson bracket is canonical, exactly.
So the converse is also true.
Yes, in fact, this is a way to check. In fact, this is part of the exercises that I'm trying to decide whether. So let me give you, then we stop. In fact, this is, so now I wrote this stuff with the Poisson bracket. So now, so if I now give you a canonical transformation, for instance, let me give you this. This is a homework. We see. Maybe on Monday. So take this one. I think it's problem 4 or chapter 9 of the Goldstein. But anyway, I write it for you. Right? I mean, this is a transformation from little q and little p, qp, qp, to big Q and big P. Imagine that you have a problem, and then you have discovered that if you do this transformation, the problem goes into a trivial one with the constant Hamiltonian. So you are now very eager to prove that you can do that. So is it canonical? And I guess the other problem with the same question, is it canonical? This is problem 15 of chapter 9. So this is problem 4. So I don't know, 19, no, it's 9-4. This is 9-15. Another set. Big Q, Q alpha where alpha is a constant, cosine beta p, a big P, is equal to Q alpha sine beta little p. So this is another, the same question. And you see that now you have at least two ways to prove that, because one way is, for instance, take for the first one, try the first way. What is the definition? Remember, it was written here of a canonical transformation. A canonical transformation is a transformation for which the Hamilton equations are preserved in form. So you have to prove that by doing this transformation, right, your equations with the new Hamiltonian k, big K, are the same form as the canonical one. Okay, this is one way. You can try that here. But as he pointed out, because of the if your new variables satisfy these three equations, by definition they are canonical. So if you compute this for the new variables, and if they satisfy that, you are guaranteed that you have transformed to a new set of variables that are still canonical. So try to write the Hamiltonian and check that the Hamilton equation are preserved in this first case, and in the second case, implement the Poisson brackets, the canonical Poisson, the fundamental Poisson brackets, and verify that if they are satisfied for little q and little p, they are also satisfied. This is what you wanted. And of course, they are not going to be satisfied for any values of alpha, beta, so you will find some condition. They are satisfied only if alpha is equal to beta is equal to some values. So on Monday, we will solve those two together. If you yeah. If you feel particularly, well, if you have nothing better to do, after you have proved for which values of alpha and beta these are canonical, then you may wonder what is the generating function of this canonical transformation. And I tell you that is of the form F3. And okay, I challenge you to find. How do you find an F? Clearly, you have to mix your coordinates. You see, here is the opposite problem. Usually, you have the F, and then, by using the equations we discussed today, you find the canonical transformation. Here, you have the canonical transformation. So what is the F that generates that canonical transformation? Well, you have to mix your variables and then guess the function. We will do it on Monday.